Hello everyone, welcome to the course on electromagnetic theory and interference. In this session, we will complete our discussion about wave propagation in lossy dielectric by introducing one parameter called loss tangent of the medium. So in the previous session, we found the expression for electric and magnetic field, and from this we can observe that as wave propagates along the positive z direction, the wave amplitude is getting attenuated by a factor of e power minus alpha z. Here this alpha is known as attenuation constant, and it is going to measure the spatial rate of decay of the wave in the medium. So the rate of decay is measured in terms of neighbors per meter, or we can express in decibels per meter also. Attenuation of 1 neighbor represents the reduction to e power minus 1 times of the original value of the wave. So 1 neighbor I can convert to decibels by taking 20 log of the E value, right? Y20 it's a voltage, right? If it is a power, we can take 10 log. Since it's a voltage, 20 log of E will give me 8.686 dB. We already found the expression for attenuation coefficient. In that expression, if you substitute for a lossless medium where conductivity is 0, we will get attenuation turns out to be 0, because here root of 1 plus 0 and outside minus 1, 1 minus 1 turns out to be 0, entire product is 0. So what it infers for a lossless medium, the attenuation, so wave is not getting attenuated as it is getting propagated, right? The quantity beta is called phase shift per unit length, and how will you measure the phase shift? By radians per meter. And this beta, the phase constant, is also called wave number. In terms of velocity and wavelength, the beta is related as below. Velocity is equal to omega by beta, wavelength is equal to 2 pi by beta. Already we know beta equal to 2 pi by lambda, right? From that we can arrive. Now we are going to understand about loss tangent of the medium. Before that, we have to observe one more thing. Wave is getting attenuated, and there is a phase shift also. If we compare electric and magnetic field expression, E is leading the electric field is leading the magnetic field by amount of theta eta. Okay, due to the complex intrinsic impedance of the medium. So we are going to find the ratio of magnitude of conduction current density to the displacement current density. Conduction current density is a real part, so we take along the x-axis. Displacement current density is imaginary, because it is equal to dou d by dou t. If I take the phasor form, j omega instead of d epsilon e, so j omega epsilon es. If we take tangential angle of particular this, the resultant vector is having angle theta. If we take tan, it is opposite by adjacent. Opposite is conduction current, adjacent is the displacement current. So we will arrive this expression after cancelling the form, taking the magnitude part. The j term get cancelled, es get cancelled. We are left with sigma by omega epsilon. This is called loss tangent, and theta is called loss angle of the medium. So by knowing the value of loss tangent, we can tell that whether it is a good conductor or good dielectric. If tangent theta is very small, so conductivity will be very less, right? So it's a good dielectric. If tan theta is very large, conductivity will be very high, and that we can call it as good conductor. We have to note one more thing. As a wave propagate, the characteristic behavior of a medium, it depends not only on the consecutive parameters like conductivity, permittivity and permeability, but also on the frequency of operation. Why we say like that? Because a medium that is acting as a good conductor at low frequency may be acting as a good conductor at higher frequencies. So the frequency of operation also is one of the parameters for a wave to get propagated. I hope you understood about the wave propagation in lossy dielectric. In next session, we will see how to solve a given problem in this particular medium. Happy learning. Thank you, everyone.